In an acid-catalyzed hydrolysis of ester, we are trying to turn an ester, something that looks like this, into a carboxylic acid, something that looks like this. This reaction is the exact opposite of a Fischer esterification. Now, what do we need to add to this ester to turn it into a carboxylic acid? So the clues are in the name. It's acid catalyzed. There must be some type of acid in there. And also, we are trying to add this OH group to this ester. And normally that will come in the form of water. Now, where does this hydrogen add to? Since it's a catalyst, it's supposed to speed up the rate of this reaction. And the way it does that to this ester is that it protonates this carbonyl oxygen, making it more positively charged. Now this turns into something that looks like this. Why is it even important that this carbonyl oxygen is positively charged? Because pulling the positive charge towards this oxygen makes this carbonyl carbon more negatively charged. Increasing the negative charge on this carbon makes it more nucleophilic. It needs to be more nucleophilic because you're trying to add water. Water is a really good leaving group. So if you add it to a regular ester, it's going to have a hard time because water is so stable. But activating the carbonyl carbon by making it more nucleophilic, it grabs onto the water tighter than usual. And so that way, water, since it can act as both a nucleophile and an electrophile, in this case, works as a better nucleophile for this carbonyl carbon. And so what we get now, something that looks like this. Our oxygen up here is not positively charged anymore. The positive charge moved down to this added water molecule. And so now our second best leaving group is this OR group. So before this OR group can leave, we need to stabilize this molecule. Now, since we only have acid and water in our solution, we need to remove this positive charge somehow. And since water is amphoteric, meaning yes, it can be both a nucleophile and an electrophile, basically means it can act as both an acid and as a base. In this solution, there's going to be hydronium ions as well as hydroxide ions. And so you can have water as a base. You can use water to deprotonate this, making it something like this. And you can have hydronium ions acting as an acid, protonating this OR group, turning it to something that looks like this. Now this OR group is really ready to go, and so it just takes off and turns our molecule into something that looks like this. Now, final step, we need to get rid of this positive charge. And do we have something basic in our solution? Yes, we have water, and we can have hydroxide ions. Either of them will work to remove this proton, removing the positive charge, and in the end we get our carboxylic acid. Now, since this is a reaction involving a carboxylic acid derivatives, it's also called an acyl substitution or a addition-elimination reaction. So what have we added? We've added the water. What have we eliminated? We eliminated this alcohol group, and we have turned our ester into our carboxylic acid right here.